Electrochemistry, continuation of our last class. In our last class, we look into one part of electrochemistry. In short, in electrochemistry, we are dealing with the relationship between chemical and electrical energy. So last class we look into electrolysis, and this is the chemical change that results when a current or when a direct current passes through chemical or electrolyte. And under this, we look into the electrolytic cell, which is also called the voltammeter. And we also talk about Faraday's law of electrolysis, Faraday's laws, law 1 and law 2. Then we'll also talk about the use of electrolysis. So in short, electrolysis is as though we are converting electrical energy to chemical energy. So for this class, we are going to do the opposite. How can we harness chemical energy to produce electrical energy? So under this, we are going to look into electrochemical cell, and it can also be called galvanic or voltaic cell. So what are electrochemical cells? So electrochemical cell is a setup made to produce what we call EMF, electromotive force, meaning a chemical force that will drive current around a circuit, or a setup that allows a continuous flow of what? Electricity through or via electromotive force. Let's draw a typical diagram of an electrochemical cell, then we'll now explain in detail. In an electrochemical cell, or let me just call it in a galvanic cell, we have two half cells. What are half cells? In these two setups, we have electrolytes. Suppose we have let's suppose we have copper sulfate here, and here we have zinc sulfate. So these two are aqueous solution, and they can dissociate into their ions. Now it is obvious that inside this solution we have two ions, copper ion and this ion, this particular radical. Same thing for zinc ion and tetrasulfate 6 ion there. And these ions will move randomly in this solution. Now suppose this is copper plates and this is zinc plates. If these two plates are immersed in this solution, they are going to observe the following. So what will happen here will be different from what happened here. So for this copper solid. So what happened here is, for copper solid, they have two electrons in the atomic shell. They can give out to attain stability to become ion. So this copper, which is solid here, will give electron to the copper in this one. This copper plus this copper that has lost two electrons to this radical. So this copper here will lose electron to this copper and becomes copper plus. While this one cancel and become copper solid. So same thing happens for this one. This one was solid, then gives this one two electrons. Then this one becomes what? Solid, and this copper 2 plus. So at the end of the day, for copper, its plate becomes positively charged on the surface. So what happens? Copper solid will be deposited on this copper metal. But we still have excess SO4 2 ion moving about in the solution. So at the end of the day, this copper becomes positively charged. Then we have copper solid form, and they will deposit on this copper plate. Then these SO2 minus, they are negatively charged, they are anion. Then they will come and surround this copper plate. So this is what is going to be observed for copper. But for zinc, we are going to observe something different. So this zinc, this zinc solid, it has two electrons to give out. But instead of copper that give out the electron to the solution, for zinc, the zinc will leave its own electron on its plate, and zinc itself will go into the solution as ion. So at the end, we are going to have XX zinc ion in the solution. So the excess electron zinc leaves is this, while the zinc ion goes into the solution. So the excess positive ions that remain will surround this zinc plate. So at the end of the day, we are going to have this. Now the question is, what does this mean? What is the importance of this? So this leads us to the concept of what we call electrode potential. Whenever a metal is in contact with its own ion, meaning is in contact with its own solution. For example, we have copper solid in contact with copper ion inside copper sulfate. So there is usually what we call electrode potential. So in this case, for copper has its own electrode potential, zinc also has its own electrode potential, but by definition, what is electrode potential? So right, electrode potential difference, or you can say electrode potential, is the potential difference, or you can call it voltage. Electrode potential, please, right, is the potential difference developed between an electrode and the electrolyte in which it is immersed due to the tendency of the electrode to lose or gain electrons. So you can say electrode potential is the potential difference, or voltage whenever produced whenever a metal is in contact with its own solution. But the thing is, it's not always only metal. It can also be a non-metal, and it's not always a metal with solution. But for now, let us take it as this. But there's a problem. It is very difficult to measure directly, the electrode potential of each metal with a solution. Very, very difficult. So what we do is to have a baseline, to have a standard at which we measure the electrode potential. So you have to create a new unit. So that new unit is what we call the standard hydrogen electrode potential. Standard hydrogen electrode potential. And for hydrogen, its electrode potential is taken to be 0.000 volts. So that's the baseline. Now the question is, how does it come about? Now suppose here we have a solution that contains hydrogen ion. Suppose an acid. So this is a solution containing hydrogen ion. Just let's say this is sulfuric acid. Now hydrogen is a gas, unlike water that we can just dip in. So since hydrogen is a gas, we need to make it work like a metal. So we need an electrode. This time around, an inert electrode, usually platinum. So what happened? We want hydrogen gas to ionize. So we need to, put in a hydrogen bubble inside the solution to see what happens between hydrogen gas and that hydrogen ion in the solution. So we can insert hydrogen bubble inside the solution via this tube. So here we have hydrogen gas. But inside this this solution containing hydrogen ion. But here there are three conditions. The first condition is that we call them the standard condition. The temperature of this setup must be 25 degrees Celsius. The concentration of the solution should be 1 molar, or we call it 1 mole per dm cube. And the atmospheric pressure must be 1 atm, 1 atmospheric pressure. So the potential difference here is taken to be 0. So if the potential difference here is 0, or let's say the electric potential here is 0, the standard, we call it standard because of what? This condition. So the standard electric potential for this hydrogen, note this time we are using platinum, but what is happening here is hydrogen. This is inert, it's not affecting anything. So standard hydrogen electric potential is taken to be 0. So if we have a metal that also has its own electric potential, so if you compare the electric potential of every electrode, we call this electrode, with with hydrogen, so we cannot look for what we call the potential difference. We cannot have the word potential difference until we compare the electric potential of a particular setup with another. So if you now compare this electric potential setup of a particular electrode with that of hydrogen, following standard condition, we are going to get the potential difference. And this has been done for common metals. So and we are going to write the results on the board now. But before that, the question is, how can we calculate the potential difference? We have to link them together. We either link this to this, or we link this to this. But everything is always linked towards hydrogen. Before that again, let's talk about what we call half-cell reaction. Just note, for a galvanic cell, we have two half cells. So we have what we call the anode half cell and the cathode half cell. One of these are what we call electrode. They are all electrodes. So one of them will be the anode, and the other will be what? Will be cathode. And remember, this acronym still works. Crowd. At the cathode, there will be reduction. At the anode, there will be what? Oxidation. So what happens at the anode is transfer of electron to the anode. So on the anode, we have excess electron. So our idea is, how can we now move the excess electron from the anode to the other electrode? So if electron can flow from the anode to the cathode spontaneously, it means we've generated what? Current. Now if we have copper plus, before it can become copper solid, it must be reduced. So it has to gain 2 electrons before it can become copper solid. So same thing goes for zinc also. For zinc to become zinc solid, it must also gain what? 2 electron. So what we have here, this equation is what we call the half cell reduction equation. So half cell reduction equation. So for all matter, they have what we call standard reduction potential. When you see the symbol E, this symbol E actually means what? Potential difference of a particular electrode. When we compare that electrode to what? Hydrogen. So if you see the symbol on it, it means under standard condition. So this standard electrode what? Potential difference. And it's either we have oxidation or we have what? Reduction. But conventionally, we always represent, or we always put the value, or we represent the value of what? Electric potential of each metal using the reduction. So the half cell reduction potential, or we'll call it standard reduction potential. So the standard reduction potential for copper, when we compare it what? With that of hydrogen, will give us plus 0.34 volts. This for copper. Why for zinc? We are going to get minus 0.76 volts. This negative sign and positive sign, they have meaning, and we need to understand that before you can understand what we call EMF, electromotive. To understand this, anytime we place a particular electrode beside hydrogen electrode, it's either electron flows from what? That metal to hydrogen, or from hydrogen to that electrode. So the direction of flow of electron is what that will give us what? The sign. So when are we going to have plus? Is it when it flows from the electrode to the hydrogen, or from hydrogen to the electrode? Now let's answer the question. So this is the answer. Copper has a positive electrode potential, so it prefers to gain electron. Let's manage the word prefers. Zinc has a negative electrode potential, so it prefers to lose electron. So for any metal that loses electron to hydrogen, note that particular metal will function as an anode, but the one that gains from hydrogen will function as a cathode. So in this case, it is as though our anode is the negative electrode. Electrodes are either anode or cathode. Anode is taken to be negative electrode, cathode to what? Positive electrode. This is in contrast with electrolytic cell. For electrolytic cell, anodes are positive electrode, cathodes are negative electrode. But the standard for galvanic cell is that anode is the negative electrode, while cathode is positive electrode. But at the cathode there is always reduction, at the anode there is always oxidation. So we've established that at the cathode there will be reduction. And what's reduction? Gain of electrons. So meaning for copper half cell we have what? Copper 2 plus being reduced to what? Copper solid by gaining what? 2 electrons. Why for zinc? Zinc is going to undergo what? Oxidation at the anode. And oxidation means what? Zinc solid will give out 2 electrons and it becomes what? Zinc ion. So this is what? Oxidation. So this is the reduction half cell. This is what? The oxidation half cell. Now what will be the next ionic equation? We have to add, let's add. So by adding it means copper 2 plus zinc solid will give us what? Copper solid plus zinc 2 plus. No, the electrons will cancel because they have the same value and they are at the opposite side. So the net EMF will be what? The difference between the electric potential, the standard electric potential of the cathode and that of the anode. So what will be the net EMF? That will be the potential, the electric potential, the standard electric potential of the cathode, in this case which is what, plus 0.34 volts, minus the standard electric potential of the what, anode, which is minus 0.76. So at the end we'll be having plus 0.34 minus plus 0.76, and this equals what, 1.1 volt. In two decimal places that will be 1.10 volts. But the question is, how is this achieved? This is what, copper electrode, this is zinc electrode. Note, the standard is to write the cathode at the left hand side and anode at the right hand side. Cathode before anode. So we are going to write copper before zinc. These two, how do we link them together? We link them together by using either a porous partition or a Salt bridge. And a Salt bridge can be gotten when a filter paper is soaked inside sodium chloride solution. So when the Salt bridge connect them together, then the circuit is completed. Without the Salt bridge, the circuit is not complete. So one of the functions of the Salt bridge is to what? Complete the circuits and to create what we call neutrality. So the what, back and forth flow of what, ions. So one, complete the circuit, two, create what we call neutrality. Now let us explain what we mean by neutrality. Remember here, we are going to have excess SO4 and here we are going to have an excess zinc ion. So what happens is as though there is no balance. So for that to be balanced, the excess SO4 will flow here to make the excess what, zinc plus, to form what, zinc sulfate solution. And that balances, that creates neutrality, and most importantly, complete the circuit. So at the end of the day, if you have to get let's say wire, if you connect the wire to this cathode and the wire to this anode, then we'll connect it to a galvanometer or a voltmeter. Let's say voltmeter is going to read the value. It gives us the value, it gives us the EMF, the net what, electrode potential, or we call it what, the EMF, electromotive force. For this case, it will be 1.10 if you use what, copper electrode and what, zinc electrode. Copper acting as the cathode and zinc acting as the anode. So this is a typical diagram for a galvanic or voltaic, or we call it electrochemical cell. So we need Salt bridge. So we need two electrodes, then voltmeter to read the value. So instead of using Salt bridge, we can also use what we call a porous partition. So that porous partition will not allow the two solutions to mix together, but it will allow the flow of what, SO4 2 minus ion to flow from the cathode to the anode. So it can be drawn this way. So this will be the porous partition, and here we have the setup for the cathode, then we have the setup for the anode. So these two will not mix together, but we call it porous partition because it will still allow us excess SO4 2 minus ion to flow from here to here, completing the circuit. Then via wire we can connect these together and we can read what, the potential difference between them, or the net electric potential, or we call it the EMF. And I think this explains, a basic electrochemical cell. But the thing is, this explanation will limit everything towards zinc electrode and what, copper electrode. But we have many other what, metals and ions we can consider. So we are going to write, I'm going to write on the board now what we call electromotive series, or we call it redox series. Before now, we've done the activity series. So now we are going to do with what, electromotive series, which is different from what, electrochemical series, or we call it the activity series. So here it shows metals, or let's say elements, and their standard electrode potential. So let's draw it on the table in order of what, increasing oxidizing ability. So let me clean the board. So at the cathode there will be reduction, meaning electron is going to be what, gain, and at the anode there will be what, oxidation. So meaning electron will be given out, to be deposited. So the excess electron on the anode will travel via this point. So this is how the electron will flow. So electron flow outside the anode and enters the cathode. That's the flow of electron. And what is current? Current is flow of charge. The rate of flow of charges is called what? Current. But current is taken to be positive, electrons are negative. So when electron flows this way, it means the current actually flowing in opposite direction. So it means the current is moving outside the cathode and the current is entering inside the what? Anode. So current enters, electron leaves. Current leaves, electrons enters. So the definition of cathode and anode remains. So cathode is a wire, a conductor, or a rod via which or through which current leaves or electron enter, while anode is a conductor or wire through which current enters or electron leaves. So they have the same definition. The only difference is anode are called negative electrode under galvanic cell, while cathode are positive, which is what? Opposite what we have in electrolytic cell. Now let's now talk about the electromotive series, or we call it the redox series. For the following elements, let's write out the standard reduction potential in volts at the front. Note, we want to write the standard reduction potential. For hydrogen, its standard electrode potential is taken to be 0.00. If you notice, everything above hydrogen, they have what? Negative what? Electrode potential. And those below, they have what? Positive electrode potential. Note, the one that has positive electrode potential are better to be used as cathode, while those with negative electrode potential are used as what? Anode. Note, in reference to what? Reduction. If it's oxidation, they will swap the sign. So this actually means when potassium gains an electron, it reduces to what? Potassium solid. So the potential in that case is what? Negative 2.93. Meaning electron will flow from potassium to hydrogen. That's why it's minus. If it's plus, it means electron flow from hydrogen to what? Example for copper. So if copper ion gains 2 electrons, it becomes what? Copper solid. So this positive indicates that electron flows from hydrogen to copper. That is why it has negative potential. So now, if you now want to get a large potential difference, EMF, the net electric potential difference, or the EMF, is the best for us to have the highest value is to use fluorine and potassium. So in this series, is as though potassium is the most reactive non-metal, while potassium is one of the most active non-metal. So when you check the difference, so if you have to have a setup in this case, and the electrode here, the cathode is potassium. No, the cathode is fluorine. I said the one with what? Positive what? Standard reduction potential is to be used as cathode. So we use chlorine as cathode, and we use potassium as anode. Then the EMF is going to be this minus this. The one for the cathode in this case is 2.87 minus anode. Just note, those that are above in this series are used as what? Anode. Those below are cathode. So it's not must to use those with negative potential are positive. You can use 2 with what? Negative what? Potential. We can use aluminum and tin. If I use aluminum and tin, aluminum will be the anode because it's up, and tin what? Will be down. So for this particular one, the net EMF is going to be 5.8 volts. Although I don't think there's any cell that uses potassium and fluorine, because of how active it is. It might explode. But in short, we are done with this. So this arrangement is in increasing oxidizing ability. And if you say something can oxidize, it means it can. If you have oxidizing ability, it means you are oxidizing agent. So if you are oxidizing agent, you yourself, you are what? You are undergoing what we call reduction. So as you are going down, the ability to be reduced increases. The ability to be reduced increases. And since we know that the cathode reduction occurs, so it means those that are down are better used as what? As cathode. So, quick question: if we have mercury, this mercury 2, this mercury 1, we have this mercury and we have tin, the best is to use mercury as cathode and tin as anode, because those below can undergo reduction more, this will undergo oxidation. So this is the anode, the negative electrode. This is what? Cathode positive electrode. This one will have excess electrons that will flow. So flow of electron will be from what? From tin to mercury. So this is how electron flows. Electron flows this way. So if electron flows this way, it means current is actually flowing from where? From mercury to tin. Current and electrons conventionally flows in opposite direction. Now, the standard way of representing, galvanic cell is to write the anode first. In this case, let's suppose we are using silver, tin and what? Mercury. So tin is the anode here. So it means you are going to write tin, and this tin then put what? The anode electrolyte. That's a single slash. Then double slash. We now write the cathode electrolyte. In this case, that will be what? Ag2 plus slash what? The cathode. No, the cathode are solid. The cathode is a solid, the anode is a solid, then the electrolyte. So we have what? Anode electrolyte, cathode electrolyte, and what? Cathode. Okay, what of the first one we did? For zinc and copper. For zinc and copper is the cathode. So we are going to write the anode first. Zinc is the anode, copper is the cathode. So for electricity cell using zinc and copper electrode, we are going to write the anode first. So that will be the anode, then the anode electrolyte, double slash, then the cathode electrolyte, then the cathode. So if you have this actually means zinc is the anode and copper is the cathode. How about this one we did here? For this one, we did the first one. Potassium with fluorine. Fluorine is the cathode, so we write the anode first. So for this particular setup, it is what? Potassium, then potassium electrolyte. Double slash. Then the cathode electrolyte, in this case, that will be I minus. Fluorine, that's F minus. Then the cathode itself, that will be F2, is a gas. And to get the net EMF, note, to get the net EMF, we write out the cathode first minus that will be anode. For example, what is copper? Copper is 0.34. Zinc is minus 0.76. So the answer is going to be, for this setup, the answer will be 0.34 minus 0.76. That will be 0.34 plus 0.76. So if we have aluminium and we have lead, we are going to write lead first, the cathode. The cathode first. Minus 0.13 minus 1.67. So just note, we subtract the standard electric potential of the cathode, of the anode from the cathode. The cathode is the one down the series, the anode the one up the series. Note, all this value here, they are under standard condition. When the temperature is 25 degrees Celsius, when the concentration of the solution is 1 mole per dm cube, and when the pressure is what for gas? 1 atmospheric pressure. But what if we don't have this condition? Because in real life, in reality, practically, this standard condition might not be followed. So what if we are not following standard condition? Then we have to use what we call the next equation. So let's talk about next equation. So we have a German scientist called Walter Nernst. He gave the mathematical relationship that enables us to calculate the EMF, of a particular electrode when the concentration is not 1 per dm cube. Because sometimes you might desire to use a solution with higher concentration. So consider this following redox equation or reduced reaction. So suppose the standard electric potential for this one is this, for a particular cell, that's the EMF. This one is when the concentration is what? 1 mole per dm cube. So what will be the EMF when the concentration is not what? 1 mole per dm cube. So this one is for standard condition, this one is if the condition is not standard. So he gave this particular equation. Bam. Don't be scared, eh? Most likely you won't need this. You won't need this for both Jam and WAEC. So you know what this two stand for? We said this is for the standard. So sometimes you can, okay, I think it should be here. So this molar gas constant, this temperature, absolute temperature, this number of what charge possessed by particular ion, number of electrons exchange, this F, which is what farad. So this is the concentration of C of D, and this is what number of mole they carry. Although this can also be simplified further, but we can just stop it here. So now we can let's compare electrolytic cell and galvanic cell. Don't forget, galvanic cell is also known as voltaic cell or electrochemical cell. So note the first one, in electrolytic cell, right, please, right, we use only one electrolyte. But for galvanic cell or electrochemical cell, we use 2 electrolytes. So 1 electrolyte, 2 electrolytes. Please write it out. So for electrolytic cell, salt bridge is not required. But here we require salt bridge. Salt bridge is not required. Salt bridge is required in galvanic cell. The third point, for electrolytic cell, the electrodes are in the same compartment. Why for this one the electrodes are in what? Separate compartments. Same compartment, separate compartments. For this one, cathode is negative, while the anode is a positive electrode. But for galvanic cell, cathode is positive and the anode is what? Negative. For this one, currents are used up. No. We convert electrical energy towards chemical energy. So current are used up. Current I is used, where here current I is produced. So that's why for electric cell we have a cell. But for those we don't have a cell here, we have what? Voltmeter that reads the cell, the voltage produced. Then lastly, which is most important, which is you can get from this 6 points, is that what? Electric cell converts electrical energy to chemical energy, while this converts chemical energy to what? Electrical energy. So these are 6 differences between electrolytic cell and galvanic cell. Now the next thing is, what are the types of galvanic cells that we have? During electrolysis, we talk about different kinds of electrolysis. We talk about the electrolysis of brine, the electrolysis of what? Acidified water, then the electrolysis of concentrated and dilute sodium chloride and the likes. So now let's now talk about types of what? Of cell. So galvanic cells, they are categorized into 2. So you have the primary cells, which cannot be reused, they cannot be recharged. So the current direction cannot be reversed. So, and we also have what we call the secondary cell, which are the accumulators, whose direction can be reversed. So electric cells are either primary cells or secondary cell, or we call them the accumulator. For primary cell we have 2. We have what we call the Daniell cell and the Leclanché cell. And for the secondary cell we have what we call the acid accumulator and alkaline accumulator. Or we call it the lead acid accumulator and the nickel ion accumulator. So in one of them we use acid as electrolyte for the lead acid, then we use alkaline as electrolyte for the next one. So now let's show up the following. So this first one is Daniell cell. So the primary cell, this Daniell cell, this is a zinc rod, and inside here we have a solution of zinc sulfate here. And this one is copper hot container. So this, like, you know, the cathode copper container, and inside here we have copper sulfate solution. So two electrolytes, this and this. Then these are the electrode. This one, the container itself is the electrode. So, and this itself is a pot, and it's porous. It's like our porous partition, acting like the what? Salt bridge. So this house Daniel is built. For Electrochemical, we have another setup. Although we have two kinds of Electrochemical, the dry Electrochemical and the wet Electrochemical, depending on the nature of the electrolyte. There is ammonium chloride paste or solution. If it's paste, it is dry. If it's solution, it's what? Wet. So inside here, we have the ammonium chloride paste. So since we are using paste here, this is a dry Electrochemical cell. Then this container itself is zinc. This is zinc container. So which is what? The anode, negative electrode. But in this case, for the cathode, we use a carbon rod. Carbon rod for the cathode, the positive electrode, and this one the negative electrode, anode. Same here, the zinc is the negative electrode, anode. This is what? The positive electrode. So here, what we have here is zinc sulfate solution. Sorry, this is the copper sulfate solution. Then inside here, we have the zinc sulfate solution as the electrolyte. So the electrolyte here for the anode, for the anodic half cell, is ammonium paste. So here, inside here, we now have the electrolyte is manganese oxide. Although the function of this manganese oxide is not actually as an electrolyte, it mainly serves as a depolarizer, usually mixed with carbon powder. So what we have here is a depolarizer, because what we call polarization, the formation of what? Hydrogen bubble. So in order to depolarize that, we need to use what? Manganese oxide with carbon. So they act as the depolarizer and oxidizing agent. Now, since they act as oxidizing agents themselves, it means they undergo what? Reduction. So what's happening here is what? Reduction. And outside here, what happens is what? Oxidation. These primary cells, first, they cannot be recharged, unlike accumulators, and they have two defects. The first one, which I mentioned, is what? Polarization, and there's a way you can prevent it. And the second one is called local action. So the second what? Defect in primary cell. So in detail, what is polarization, what is local action, and how can they be prevented? So local action is actually undesired partial discharge of cell caused by impurity in the zinc container, even when the cell is not in use. So this zinc container, if there are impurities in it, so the current or the PD that is ought to be generated is going to what? Be reduced. There will be loss in PD due to those impurities formed on the zinc. So these impurities can be like iron, or from local cells, and this causes zinc to dissolve slowly, releasing electron. So it loses energy, and at the end, the battery will run down very quick. So this can actually be reduced by what we call amalgamation. So we coat the zinc with acid. You can rub it with sulfuric acid, H2SO4, with a thin layer of mercury. So to prevent what? Those impurity, in order not to dissolve the zinc. So local action can be prevented by rubbing or by cleaning the zinc with what? Sulfuric acid, and rubbing with what? With mercury. And this process is what we call amalgamation. While polarization is the build-up of hydrogen gas, bubbles at the cathode during discharge, and this reduces the cell efficiency also. So in order to prevent polarization, that is when you use what? Depolarizers such as manganese oxide. So lastly, let's talk about accumulators. Like I said earlier, we have to type the acid accumulator and the alkaline accumulator. Like I've said earlier, accumulators, they can be recharged. After they discharge by giving us current, we can use external current to recharge the accumulator to be used later. So they can be recharged, or we can call them rechargeable batteries. But the normal fuel or the dry cells are single use, and they cannot be what? They cannot be recharged. So the electrolytes used in acid accumulator is sulfuric acid, while here we use what? Potassium hydroxide as the electrolyte. while this can only generate about 1.2 to 1.3 volts, so this can generate up to what, 2 volts. So lead acid accumulator generates higher what speed. So this give higher current output, yes, it give higher, but this one it give lighter but steady output. So anytime you need steady output, we use what, alkaline accumulator. If you need higher, we use what, acid accumulator. For example, in cars and in solar storage, we use what, lead acid accumulator. But in portable electronics like and torches, so we use what, alkaline accumulator. I think with this we can come to the end of the lecture.